Hello, welcome to the first video in Momentum for the Physics uh, A2 course. Um, what is it? It is AQA I cover, but it's applicable to other exam boards as well. So, going over momentum, the first thing you want to know about momentum is that momentum is represented by P. And we have these two equations here which we'll be focusing on throughout this video. The first one is the equation for momentum, where momentum is the change of mass times velocity, so mv. And we also will be focusing on this equation, which we'll cover perhaps more so in the second video, but we should know that force is equal to the rate of change in momentum, where the rate of change in momentum is the change in momentum over the change in time. If you wanted a definition for momentum, you could say the quantity of motion of a moving object. So if momentum is the quantity of motion of a moving body measured as a product of its mass and velocity. So change to the laser pointer. This down here, mass and velocity there. That's simple enough. Just those two equations to understand, and we'll also be looking at how to rearrange these in some certain ways. But the first thing I want to look over is the three laws of motion that Newton's three laws of motion that we'd be looking at. So the first law we're looking at is that an object remains at rest or in uniform motion unless acted on by a force. So unless an object is acted on by a resultant force, it will remain at rest or in a uniform motion. And so from this, we can know that a force will be needed to change the momentum of an object. Okay? Because if in order to change momentum, either mass or velocity is going to have to be greater than zero, or it's going to have to change itself. To change momentum, one of those is going to have to change. And if we want to change the motion of an object, it has to be acted on by a resultant force. And so to change velocity, we have to act on that object with a resultant force. Another thing we can say from this law is if there is a constant momentum, so if you know that an object's momentum is not changing, then it's safe to assume that there is no resultant force acting on the object. So there's no resultant force. Okay? So like the example, if a mass and momentum, mass is usually constant, but we'll get some situations where it isn't, but we'll move on to that later. And momentum are constant in a system or in an object, then you can assume that velocity will also be constant. One thing, I don't want to sound patronizing, but one thing that you don't want to slip up on in questions, because they'll word it in some certain ways to make it confusing. But if you have an object and it has a constant velocity, it means that there's going to be no resultant force acting on that object. So it has a constant mass and a constant velocity. There's going to be no resultant force acting on that object, but that doesn't mean that its momentum is going to be zero, because it'll still have momentum. So if velocity is greater than zero, it will have a momentum as long as it has mass, and mass is usually constant, but then again we'll get onto when mass changes. Okay, so just to let you know. So that's the first law. That's an easy one. Moving on to the second law. I will cover the second law later on in this video a bit more detail, but I want to just get these three laws down before moving on to more detail. So the second law is the rate of change of momentum is proportional to the resultant force. So this is a law. From what I understand, you can't prove Newton's laws. They're just that, laws. So the resultant force is proportional to the rate of change of momentum, and you get it from this equation with my really badly drawn proportionality sign. So force is proportional to the change of momentum over the change in time. In other words, the rate of change of momentum. Okay, that's all I'll say for the second law for now, but we'll go on to why this is in a few minutes. And so the third law, this is probably the most recognized one. When two objects interact, they exert an equal and opposite force on each other. So every action has an equal and opposite reaction. So this follows on nicely to the principle of conservation of momentum, which is a key concept in the momentum topic. So this will come up quite a lot. So for a system of interacting objects, sorry that we're rushing through all these definitions, by the way, but we want to get through the video. So for a system of interacting objects, so if you have two objects that are interacting, or more than two, it's a system. The total momentum remains constant, provided there are no external forces act on the system. So linking back to Newton's first law, if there is a resultant force acting on an object, then its momentum is going to change. But if you have a system of interacting objects, and there's no resultant force acting on them, so no new forces are acting on them, then the momentum that they started off with will remain constant. It's not going to change. Okay? And so if we have an example here, we have object A and object B. Object A is moving quite fast, and object B is stationary. That's stationary, fast. They have the same mass. Object B looks bigger, but perhaps it's just less dense or something. They have the same mass, and object A is moving at velocity 1, and object B is moving at velocity 2. One thing we can assume about this system is that object B's velocity is going to be 0 because it's stationary, so it's not going to be moving, is it? It's a head-on collision, and it's an elastic collision. We're going to talk about elastic and inelastic collisions later in the second video, but I really should be timing this video actually. Oh well, never mind. I'll just, hopefully it won't go over like too long. Elastic collision. Elastic simply means that no energy has been lost to the surroundings in the collision, so there's been no energy lost, which is usually you'll assume that no energy is lost when you're answering questions, to make it simpler. So, actually, I'll move on here. I'll pause the video for a second and just try and think what's going to happen when object A collides with object B, considering it's an elastic collision. So, moving on. When object A collides with object B, object A will exert a force on object B, and object B will exert an equal and opposite force on A. And so A will come to a halt, and it will have all of the momentum in A will be transferred to object B. And so now object A will be stationary because it's been cancelled out. So its velocity is now 0, and object B is moving forward with a velocity that object A originally started off with, because no energy has been lost to the surroundings. It's transferred all of its momentum to object B. Now object B is moving. Let's imagine they're in space as well, because you could say that object B wouldn't roll very well compared to object A. But they have the same mass. But what if, say, object B were to have twice the mass of object A? The same thing would happen. It's an elastic collision, so all of the momentum is going to be transferred. But if object B had 2m, say, so twice the mass, we go back to this original equation, P equals mv. If we were to rearrange it to find the velocity that object B is going to be moving at after they've collided, it would be P over m is equal to v, so the momentum over the mass. And if mass is 2 times greater, then it's going to be momentum over 2 times mass. And so simply, it's simple rearranging, you know. Object B is going to be moving at a velocity half that object A was moving at originally. So that's that. That's quite simple. Elastic collision, so momentum is conserved. So object A will have the same amount of momentum that object B rather will have the same amount of momentum as object A had to begin with. So that's that. That's Newton's third law. Moving on. Back to the second law, I'm going to be explaining a bit more about that. So the rate of change of momentum is proportional to the resultant force, as we said before. And you saw that equation at the start, F is equal to delta mv over delta t. And that can be derived from this second law, the rate of change of momentum is proportional to the resultant force. As you can see here, the force is proportional to the rate of change of momentum. And I'll tell you now why this is true. So if you have force, we know this is the law, Newton's second law. Force is proportional to the rate of change of momentum. This change of momentum over time taken is the rate of change of momentum. And if ignoring force for now and just looking at this, we can put it into symbols here. So we can have mv minus mu, where v is the final velocity and m is the initial velocity. And so the final momentum minus the initial momentum is going to be the change momentum over the change in time. It's important to remember that in this circumstance we assume that mass is constant, because it usually will be constant, and we'll talk about when it isn't. But So if mass is constant, is if m is the same, we can factorize it out of these brackets, and so it can be m is now times by v minus u. V minus u, remember, just being delta v, so the change of velocity. And if you can look at, I've circled around this bit, not very well. I say circled, more like a weird. It's like a Pokemon, one of the the little mole ones. But so delta v over delta t, as you know from GCSE and possibly earlier in the year, it's quite well known. Delta v over delta t is acceleration. If you didn't know that, now you do. So that can simple down to a, which is acceleration, and so we get ma, mass times acceleration, is the same as the change in momentum over the time taken, because it just simplifies down to that. Okay, and so if we bring force back into the proportionality now thing, force is proportional to mass times acceleration. Okay, and if you've ever done proportionality, if you haven't, it might be worth going and doing a bit of that. But really, it's not that hard to understand. We want to change this into an equation. We have to put in a constant of proportionality. In this case, we'll call it k, as it usually is. K for constant with a k, perhaps. So k is the constant of proportionality. So now we can say that F is equal to k times mass times acceleration. Again, the force is measured in newtons. And so 1 newton, the definition of a newton, so 1 newton will give an object of 1 kilogram an acceleration of 1 meter per second, or 1 meter per second squared. Okay? 1 kilogram, an acceleration of 1 meter per second squared. That's 1 newton. And so if we have 1 newton, if F is equal to 1 newton in this case, we can assume that k is going to be equal to 1, because in order to get 1 on the other side, k is going to have to be 1, mass is going to have to be 1, and acceleration is going to have to be 1. 1 times 1 times 1 is equal to 1. And as k is a constant, k will always be 1, because it's constant. And so, in that sense, 1 times anything is just itself. So we can kind of just get rid of k. And so we're left with force is equal to mass times acceleration. And this can be changed back into the equation. Force is equal to mass times the delta v over delta t. Remember that it's important to remember, though, that this is applicable when mass is constant. When mass isn't constant, say, so mass changes at a constant rate, and velocity is constant instead. So mass could be changing if we have a rocket, say here, and it has a fuel tank, and it's combusting the fuel and lifting the rocket. The fuel is going to combust, and so it's going to get lighter as the fuel depletes, or whatever. So as the fuel goes away, the rocket will get lighter. So mass is changing in this case, and it's exactly the same equation. It's quite easy. It's just F is equal to velocity, which in this case is constant, times by delta m over delta t. Delta m being the mass of the hot gas lost per second, or the mass of whatever is being lost per second. Okay. Yeah. So in these questions, I would recommend going over a lot of example questions, especially on where mass is changing, because they can be complicated sometimes. So another thing to look out for is, say they give you you're trying to find the velocity, and you've got the initial mass and the final mass, and you've also got the time taken, and you've gotten the force, but it gives you the force of the thrust of the rocket, and you need to know the force exerted by the rocket to eject the hot gas, or the force exerted by the rocket to eject the fuel, So because the mass that's changing is the fuel, not the rocket itself. And so if we have the thrust, because of Newton's third law of motion, where every action has an equal and opposite reaction, we can say that it's going to have the same magnitude as the force exerted by the rocket to eject the hot gas. So just to let you know that one. Remember, do some questions on this. Just do past papers, really. You'll get the hang of it after that. But moving on to impulse. Impulse is something that it's quite simple to understand impulse. We'll be talking a bit more about impulse in the second video, but impulse is the effect of a force acting over a period of time. So if a force is acting on something for a period of time, you can measure that with impulse. It's usually represented by Newton seconds, NS, or it can be represented by kilogram meters per second, but I wouldn't represent it in that way because it gets confusing, because kilogram meters per second is how you represent momentum, P. So the equation for impulse is literally just this equation rearranged. F equals change in momentum over change in time. So F delta T is equal to change in momentum, delta mv. So you can see why it's measured in Newton seconds, because force is measured in newtons and time is measured in seconds, i.e. it's Newton times seconds, Newton seconds. And you'll often come across these kind of graphs when you're talking about impulse, force time graphs. The area will be equal to the impulse, because if you have the base here, which is time, and you have the height in force, timesing them together, you've got force times time, change in time, and so F delta T, which is impulse. But one thing that's useful is to know is that impulse is pretty much it's the same thing as momentum, really. It's so the area under the graph here can be, you can find the impulse, which is the area under the graph, but that's how much momentum there will be also. So moving on to a question to finish off this video. Sorry, I couldn't blank this last bit out. I'll just move that in front of it so you can't see. A rail wagon of mass 4,500 kilograms is moving along a level track at a speed of 3 meters per second. It collides with and couples to a second rail wagon of mass 3,000 kilograms, which is initially stationary. We'll move on to what couples means in the second video, but it simply means that it connects, basically. So they'll connect together. So it's almost as if they've become one object now. Calculate the speed of the two wagons immediately after the collision. So what you've got is the mass, you've got the speed at which this first wagon is moving initially. So by that you can calculate its momentum. And you've got the second rail with a wagon mass of 3,000 kilograms, which is stationary. And so you can assume that because it's stationary, it's going to have a velocity of 0. So you can calculate the momentum of that one as well. So now you can calculate the speed of the two wagons immediately after the collision. So this is after they've coupled. Coupled kind of meaning like they've become one object almost, because they're now stuck together. And I'll give you a second to pause the video, and then I'll move on to answer the question. So pause the video, try and answer that, and then I'll come back. Okay, and I'm back. Well, I never left, but here I am. I'll move this away. So the first thing we want to do is the total initial momentum. Because of the principle of conservation of momentum, remember, so this heavily used the principle of conservation of momentum, remember that, which we explained earlier on in the video, and we want to move back just to re-watch it maybe. The total initial momentum will be equal to the initial momentum of A. Oh, where's my laser pointer? The initial momentum of A plus the initial momentum of B. And we know the initial momentum of A is going to be 4,500 times by 3, that's speed, and B is going to be 3,000 times by 0, because it's stationary. And so the the total momentum of the system before collision is going to be 13,500 kilogram meters per second. And onto this, I'll just move this way. Onto the next bit, the total final momentum that's going to be after the collision. This is now, so the final momentum after the collision is going to be the total mass of A plus B, because they've coupled, they're kind of like one object, so you add their masses together, times by the velocity v after the collision. So this velocity is what we're trying to find. We don't know this velocity, but we're trying to find the speed of the wagons immediately after the collision. So if we have their masses, add them together, times it by v, we'll have 7,500 times by v. Because of the principle of conservation of momentum, the momentum before the collision is going to be the same as the momentum after the collision. Remember. If you don't remember that, go back to when we talked about principle of conservation of momentum, and it'll hopefully be explained. But So what we can say is that 7,500 times by v will be equal to 13,500 kilogram meters per second, the momentum. Because this 7,500 times by v is the same as, it's mv, which is momentum. And so we can rearrange to find v, as you can see here. And so we know that velocity is going to be equal to 1.8 meters per second. Well, if I didn't explain anything as you would have liked to, feel free to comment in the sections below and I'll try to get back to you. This is the first video, so we'll be going into a bit more detail in the second video on some things. But hopefully that's helped you out. And yeah, any questions, just ask, and I hope it goes well for you. Thanks for watching. See you in the next video. Bye.